Hello everyone. Today I'm going to talk about graph isomorphism and lattices. As you know, this lecture won't be included in your final exam, but these two topics are important, especially if you want to continue in advanced level related to discrete computational structures. We already talked about adjacent vertices. But let's remind ourselves about what was such vertices. Well, what we are talking about when we say adjacent vertices, because you already know about adjacent matrices, and they could be both for undirected and directed graphs. But when we talk about adjacent vertices, it's different, and already we talked about it. So two vertices U and V. So we are talking about two vertices in an undirected graph, not directed one. And this graph is called G. They are called adjacent or neighbors in G if U and V are endpoints of an edge E of G. Such an edge E is called incident with the vertices U and V, and E is said to connect U and V. Okay, we needed this part of the definition related to adjacent vertices so that we can talk about graph isomorphism. So we often need to know whether it's possible to draw two graphs in the same way. That is, do the graphs have the same structure when we ignore the identities of the vertices or not? So it means that when you have two graphs with specific vertices and they have specific titles too, they have different names like A, B, C, D, or they have names as numbers and we call them title. So in terms of their structures, whether they are isomorphic or not. And that's what we are talking about in terms of graph isomorphism. So here's the official definition. The simple graphs, so we are talking about simple graphs. Do you remember what they are? Simple graphs. It means that if you have two vertices, we should have maximum one edge between them. It could be no edge between them or one. It cannot have, for example, multi edges, and we cannot call it a multigraph. Or one vertex cannot have a loop like this. So these ones we call simple graph. The simple graphs G1 equal to V, for example, vertex set and edge set. You remember each one of them are sets. V1 and E1 is the name of them, and you remember whenever we talk about definition of graphs, we show them by two components as the set of vertices and edges. So G1 and G2, both of them simple graphs, are isomorphic if there exists a one-to-one and onto function. So we are talking about a function which has two properties. It should be onto and one-to-one. We talked about it before when we talked about functions. It means that you can find the inverse of a function if it is one-to-one and onto. And this one actually has this property. So from V1 to V2, so we are going from V1 to V2, with the property that A and B are adjacent, so we needed adjacent vertices because of this. In G1, so A and B are two adjacent vertices in G1, if and only if FA and FB, we are talking about this function and we are assigning A and B inside this function. It means that from G1 to G2 we are talking about, and in terms of their vertices. So from this set inside G1, we are going to this set in G2, and we use this function to do that. This function should be one-to-one and onto. It means that it is possible to find the inverse of this function as well and come back from V2 to V1. So let's go back to this part. G1 and G2 as two simple graphs are isomorphic if there exists this function with this property from V1 to V2 with the property that A and B are adjacent in G1, so they should be neighbors, if and only if FA and FB are adjacent. So when you find two neighbors in V1 inside the graph, then if you apply this function, you should find exactly two neighbors by using these two functions. Otherwise, it's not possible. So it should hold for all A and B in V1. So any elements you take from these vertices should follow this rule. So such a function, we call it isomorphism. And also two simple graphs that are not isomorphic are called non-isomorphic. Isomorphism is important. Why? Again, I remind you, because it shows the similar structure between two graphs. When you want to model a phenomenon using discrete computational structures, this term is very important to know, graph isomorphism, so that when you change the title, we won't be confused about that. When you change the shape of the graph, you won't be confused structurally about what's going on. So this is very important. Like these two graphs are isomorphic. And why is it the case? Because you can find such a function that you will find exactly when you have, for example, these two vertices here. If you apply the function, you should find exactly two vertices that have the same property. Again, they are adjacent. It doesn't mean exactly it should be V1 and V2. Don't be confused about the titles. It could be, for example, maybe we are talking about V3 and V4 here. Okay, so these things needs practice, of course, and inside the book I will show you that which part you can read in order to know exactly what's going on. But since we don't deal with it in the final exam, so I don't go through the details, but I just mentioned that these topics that I'm talking about today is very important, especially if you want to know about advanced discrete computational structures, how to model them, and hopefully if someday you want to continue in your master program, then we can talk about them in details. But anyway, when you go through the book, and I will tell you which chapters to read, you can ask me your questions if you have any. So the next thing I really want you guys to know about is related to poset. Poset, what do we mean by that? A relation R on a set S is called a partial ordering or partial order if it is reflexive, antisymmetric, and transitive. You already know about relations. We talked about it. And you already know about these properties. It's not hard to understand about this definition. So a relation with these properties, we call it partial ordering. Now, a set S together with the partial ordering R, so we are again talking about the set and the relation with these properties, and you remember this relation gets its elements from this set. So it cannot have, for example, elements from other sets. So S and R should be together. And so these two together, they are called partial order set or poset. And it's denoted by a pair. You see, they are together. We are talking about the set that we found the relation from this set. It means that you get elements of this relation from this set and the relation itself. So these two together, we call it a poset. Members of S are called elements of the poset, obviously. We needed to know about posets because we want to talk about lattices. So a poset in which every pair of elements has both a least upper bound and a greatest lower bound is called lattice. So you may ask me, what are these two terms? In order to understand them perfectly, we need to know about topology in mathematics. In pure mathematics, when we want to start talking about discrete mathematics, then I should start everything from relations. So for this course, we started from topics related to logic and sets, functions, and so on. But when we teach discrete mathematics to mathematicians, then right away we should start from relations, and then by knowing the topology that we already know that these students already took that course. So we can easily talk about lattices and continue. But for computer scientists, we don't go that much through the details because we should know that much more than the things that we already know. But anyway, it is well defined in your book. This book is perfect, the one that I shared with you. It's well written and it's simple. So it's not very hard to understand. So if you are interested, please go through that. And this is the definition of lattice. But why we need lattices, especially if you are interested to know about Boolean algebra, because without knowing about lattices, it's not possible to cover Boolean algebra. This is the prerequisite for that somehow, we could say. And for different modelings, we use lattices as well. So when you will be comfortable working with lattices, you should distinguish between these graphs. And these graphs, by the way, we call them Hase, or as Swedish people call it, Hase diagrams. Again, to know which kind of diagrams is Hase is well explained in the book. I will show you where to read them. So when you want to check with yourself whether you understood what are lattices, check with this slide. Check whether you understand why A and B are lattices, but B is not. Okay? So if you are interested, you can go through these chapters. Section 9.6 of chapter 9. Here, the author explained very well about lattices, about posets, and everything is there. You can take a look. Even Hase diagrams is there, some examples related to that. So if you have any questions about that, you can ask me. Also, after final exam is possible because it's not related to final exam. You can even postpone reading them after you pass this course, and then you can also ask me your questions about it. It's never too late, and I will keep checking my emails anyway. And from chapter 10, 10.2, this section is related to terminology related to graphs. And we use some of them in 10.3, which is included in the final exam. We talked about it last week. And we use those terminologies. I didn't talk about all of them because not all of them were mentioned in 10.3, which was in the syllabus of the course. But this section, I really suggest you guys to take a look to know more about the terminologies that we use in graphs. And 10.4 can be useful as well because you're already familiar with graphs. And this section, although not included in the final exam, not included in your course syllabus, but it can be useful. Okay, guys, if you have any questions, please let me know. Otherwise, I will see you next Wednesday. We will talk about your assignment number 11. And don't forget to go through 10.3 subsection in the book. This one is very important because it's included in the final exam and we talked about it in details last week.